All right, I'm going to be going through the first packet in the Physics Basic Skills unit. This is mostly about graphing and how to scale a graph and how to find a line of best fit and things like that. So if you're looking for more help with those sorts of skills, this is the video for you. So this first problem here has us graphing a system where there are some cells and the temperature is being varied. And based on the temperature, we get some different amounts of yeast cells that are grown. And so the first step on any of these problems is just to plot the data. But before you do that, you need to figure out what a good scale would be. And so then the next thing we'll do is we'll look at our graph that we have available, and you have to count the boxes that are there. And you'll find that in the graphs that I typically use for these, it's a 20 by 20 graph. So there should be 20 boxes. In the problem, it specifies that you should have 50 units along the x-axis or the horizontal axis. And in class, I recommended that we try and have the vertical axis, the y-axis, go up to 60 for the number of cells. And you'll see why kind of as I go through this problem. So the first thing here, go ahead and plot the points. We are plotting number of cells on the y-axis and temperature on the x-axis. And so 50, if we're going up to 50 on that x-axis, and there are 20 squares, I think a good way of starting this out is you say, all right, it has to go up to 50, and we have 20 squares, so you divide 50 by 20, and here you get 2.5. So each square should be 2.5 units, or I think it's easier to think of it as being every 2 squares is 5 units. All right, so if each box represents on the x-axis 2.5 units, then if we go 2 boxes, we get to 5, and then 2 more boxes gives us 10, and then 15, and then 20, and then 25, and then 30, 35, and then 40, 45, and then 50. And so then we've scaled it so that we've got perfectly 50 on there. Now, you won't always have to do that. If you had wanted to make each box 3 here and scaled it so that it ended up in 60 at the end, that would have been acceptable as well. But this is really the most ideal for taking up the entire graph. Now, as I said, I recommend you do go to 60 on the vertical axis. And so go ahead and if there are 20 boxes here on the vertical axis and we're trying to go up to 60, you say 60 divided by the 20 boxes, and you get 3 units per box. Okay, so each one of these boxes is going to be 3. I don't think that you should label every one because I think that that gets really messy. And so I'd recommend you label it like every 6 or something like that. Skip 2 boxes, label 6. Skip 2 boxes, label 12, etc., etc. So I'm going to go ahead and do that, and I'm going to do some labeling of the axes, and then I'll come back. All right, so now the axes are labeled, and I've got it marked, every other box so that I can clearly see where I am. And so the next thing I need to do is I need to plot my data. And so this first point here, it says it has a temperature of 5 and a number of cells of 52. So I find that I go on temperature and I look up 5 on that axis, which is the x-axis, and I look up and find 52. And I see here that it's going to be something like right here. All right, and then, I'll just go through here and I'll plot all the other points. So like the next one would be 1045. So I go to 10. On the temperature axis, I go up to 45 on the number of cells axis. Oops, that's 1048. All right, and there's that point. And so I'm going to go through and plot the rest of these points, and then I'll talk about the next step. All right, so there are all the data plotted, and the next thing that we need to do is we need to draw a line of best fit. And so the line of best fit is going to go sort of through the center of all these points. It's supposed to identify as a general trend what this line would look like if these are all in a linear relationship. And so it is what the things it is not is it's not connecting the dots. So make sure you're not connecting the dots. And Another thing, this one clearly wouldn't go through the origin 0, 0, but don't force it through the origin. It just needs to be kind of a general trend of the data. So I'm going to go ahead and construct what I think looks like a good line of best fit here. You can see here that the line of best fit goes through the data. There are a couple points above, a couple points below, but it, generally speaking here, shows the general trend. So this is what I'm going to use for my data. So after I've got the line of best fit, I'm going to continue on to do the rest of these. I say after this point, ignore the data points. The line is what we're working with. So we're going to be working with the line the entire rest of the time. Don't look back at those data points at all. So for C, it says, estimate how many cells would be present at 47 degrees Celsius and explain. So what we're going to do here is we're going to come up. We look at our line of best fit, as I said. We want to find 47 degrees Celsius. So 47 is right about here. All right, and then you're going to trace that over and see what that would be. It looks like if you trace it over, it's somewhere here just below 9. So I'll call that something like 8 cells. All right, so if you trace this over here, it hits there at such a point so that it looks like it's around 8 cells at 47 degrees Celsius. So this would be 8 cells by inspection. All right. Now we'll go on to the next question here. It says, determine the value and units of slope for your graph. Use x's on your graph to indicate the 2 points that you use to calculate your slope and provide an explanation for what the slope means. All right, so we need to go back here and find our graph. And we need to calculate the slope for it. So the strategy here is you need to find 2 points where the line of best fit intersects kind of well with an intersection here. And so I see, as one example, a nice intersection is right here, it looks like. All right, we've got the line hitting directly 40, 15. All right, so I'm going to use that as one of my points, 40, 15. All right, and then I find another point. I want it on the other side of the graph so that things work out pretty nicely, and I don't have as much error if it's not, if it's not as close together. So I'll find a point that's kind of over here. It looks like we've got another nice point sort of right here. All right, that looks like it is at 7.5, 48. Now to get the slope from these 2 points, we have to do delta y over delta x. Okay, the change in y, we're looking at how these last ones change. So going from 15 up to 48, that is a change of 33. And then going from 40 40 here, down to 7.5. That is a change of negative 32.5. And then you'll put that in your calculator and see what it gives you, because we don't want it written as a fraction. And I get negative 1.02. Now, it should be noted that your value could be different from this because you'll have a different line of best fit and you will have chosen some different points here where it intersects nicely, but it should be something near negative 1.02. The next thing we have to consider is the units on this slope. Now, remember here we said that slope is calculated by saying delta y over delta x, and so the units go the same way. We take the y units and we put them over the x units. On the y-axis, that's the number of cells. Our units is cells. On the x-axis, our units are degrees Celsius. All right, and so that gives us units here of cells per degree Celsius. And that is your slope. Here I'll go back to the other page and I'll write out sort of my interpretation here of what this slope means. So generally speaking, when you see cells per degree Celsius, you could read that negative 1.02 cells per 1 degree Celsius. And that might help you think about what this would mean. But I think a pretty good interpretation of this would be that for every increase by 1 degree Celsius, there are 1.02 fewer cells grown. Now, you could say that in a few different ways, but it should have the same general idea. As a generic form, the slope is always going to be for every change in 1 for the x variable, this is the change for the y variable. So in this case, for every change by 1 degree Celsius, there's 1.02 fewer cells grown. All right? But it's always for every change in 1 for the x variable, there is this change in the y variable. This next question asks us to determine the vertical intercept. And so this actually, there's a lot of mathematically complicated ways that you could go through and do this, but I actually think the better way is to just go back and look at your graph and see what the vertical intercept is. So we go back here and we look at the graph that we made, and we see, all right, on the vertical axis, the intercept is right here. Now, if I look at that axis, I say that, that's just above 54, so I'm going to call that 55, all right? And in a second here, it's going to ask me, like, what are the units on this and what's my interpretation? So looking here, this axis is measuring the number of cells. So 55 here is the number of cells. And then we need to figure out what's special about the intercept. Well, the intercept is when you have a 0 on the x-axis. That's the definition of a y or a vertical intercept. It's when the x variable is 0. So what we have here is 55 cells, and that is when the temperature is 0 degrees Celsius. Okay, so that's how we interpret our intercept there. And again, generally speaking, the vertical intercept is going to be the y value or the vertical value when x equals 0. That's the definition of a vertical intercept. For f here now, it wants us to go ahead and write an equation for this graph that we've created, and it needs to be easy to interpret. And so basically what I'm saying there is don't use x and y. All right, I want you to use actual variables that make sense in this case. And so what I recommend is you start with y equals mx plus b. All right, that's your slope-intercept form for a line. But now we're going to be putting in things to make it more meaningful. So y, that's the vertical axis. If we look back at our graph here at the vertical axis, all right, it has cells on it. So a good variable for that would be c to represent cells. Now the slope, for me, I got negative 1.02. Remember, yours might be slightly different, so just go with whatever you had. And then the x variable in this case is the temperature. In science, we use a capital T to represent temperature. All right. Next, we have to add the intercept. For mine, I got 55. Your value for that might have been slightly different. It was wherever your graph, wherever your line of best fit intercepted your y-axis. All right? And then we've got our equation here. The one thing left to do is I think that you should make a key for the equation, so if someone was looking at it, they could interpret it a little bit more easily. So I say C equals the number of cells grown and T equals the temperature. Now, it's clear here that number of cells grown is going to be given in number of cells. All right, but the temperature is a little bit more ambiguous because there are different scales of temperature. So I need to say that we're talking about degrees Celsius here. So anybody who's looking at this equation would know to plug in the temperature in degrees Celsius. For part G here, it says that we need to determine how many cells would be present at 42 degrees Celsius. So we're going to be using our equation now, and we have to think about what they just gave us. 42 degrees Celsius. That's the temperature. So I'm going to be using this equation, and I'm going to be plugging in 42 degrees Celsius for temperature. So C is still an unknown. So C equals negative 1.02, and then I'll plug in 42 there for the temperature. And then plus 55, because we've got our y-intercept there. All right. Now at this point, I'd throw that directly into my calculator, and I get 12.2 cells. Now again, you might have something slightly different than this because your equation should look different depending on your slope and your y-intercept, but it should be something close to 12.2. Next, we'll move on to these challenge questions. This first one here, it says, now imagine that you have 28 yeast cells, and it's asking you what temperature you would have if that were the case. So in this case, they've given you the yeast cells, and they're asking you to solve for T. So I'm going to plug it in using the same equation from above, except this time I have C. So 28 equals negative 1.02 times T plus 55. All right. Then what I'm going to do is I'm going to subtract 55 from both sides. And I get 27 equals negative 1.02 T. All right, now I'm going to divide both sides by 1.02, negative 1.02. So that will cancel. Sorry, this should have been a negative 27 up here, but yeah, dividing both sides by negative 1.02, I get 26.5 degrees Celsius equals my temperature. These last two questions are more conceptual. So it says, what would the graph look like if the temperature had a larger impact on the number of cells? For instance, if there was a change of negative 5 cells per degree Celsius. All right, so here when you look at this, it might be a little confusing what that means. But when you see cells per degree Celsius, that should sort of remind you of something that you saw earlier. So if we look up here at the top of this page, we see that cells per degree Celsius is the units on our slope. And our slope here was negative 1. All right, it's saying, imagine if this change was negative 5 cells per degree Celsius. And so what's really happening here is that the graph would have a steeper slope. And then this last question here said, what would your graph look like if there were more cells at 0 degrees Celsius, but the net change in cells per degree Celsius remained the same? So for this one, what we're looking at, we've got more cells at 0 degrees Celsius, and that should look familiar to you as well. What we're talking about, the number of cells at 0 degrees Celsius, that is the vertical intercept. So in this case, it says more cells at 0 degrees Celsius, which means that our vertical intercept would be higher. And then it said the net change in cells per degree Celsius. And again, this is written out in words, but we're looking at cells per degree Celsius, which is your slope, all right? And it says that remains the same. So what we have here is we have a higher vertical intercept, but we have the same slope as our original graph. And that is the full process here in terms of this data analysis. We're going to go through a lot more examples of this in the next few days, but make sure that you understand this as we go, because each step is going to be getting a little bit harder and a little bit more independent. So if after watching this video you're still confused about anything, you can go ahead and come in and I'll talk to you. Otherwise, ask questions of your peers and just make sure you're in class and engaged every single day.